Alright, in this video we're going to take a look at what we call Prim's algorithm, and it's just a way of working out the minimum spanning tree of a network graph. And an algorithm is just a fancy word that means a process or a procedure for doing something. So we're going to go through and see how can we apply this to any network graph to work out the minimum spanning tree for it. So having a look at our network graph here, where are we? Right, we've got these vertices A, B, C, D, E, and F. So what would be the minimum spanning tree for this? Alright, so Prim's algorithm, the first step is pick any vertex. It does not matter which one you pick, okay? I'm going to start with A because that just seems like a good place to start. So if we were to start with A, and you've got to look at from that point now, from your starting point, and say, alright, of the edges that come out from that point, which one is the shortest? So I can see AB there. I can see AD runs along there, it's 5, and I can see AF runs along there, and it's 6. So it's pretty obvious that to me that the shortest one there is AB equals, in this case, 2. And I'm just going to try and reproduce it under here. So if I was to go AB, something like that, we're going to go AB is 2. All right. So we've now got covered that edge there. I'm just going to color that one in badly, but you got the idea. So now I've got A and B as part of my spanning tree. So I have to look at both of them now. So I'm just going to repeat the same process and find the shortest edge, but which is the shortest edge that either comes off A or B now, because they're both included in my spanning tree. So from A, I've got 5 and 6 coming off it. From B, I've got 6 and 8. So it's pretty clear to me that that one there, is now the shortest, going from A to D. So from A to D equals 5. So let's just reproduce that on our little sort of mud map down here. Sorry about that. Let's go A to D. Okay, and that's 5. So we're starting to build up our little spanning tree down here. We've got B to A. Let's just make that a little bit clearer. And now I've got to include D, okay, because I've got my spanning tree going through D. So repeat the process again, looking at A, B, and D. What is now the shortest edge that comes off? Well, from B, I've got 8 and 6. From A, I've got 6. And from D, however, I've got 6, 6, 7, 3, and 3. So that's pretty obvious that this one now becomes the shortest between D and C. It's 3. So I'm going now from D to C, 3. And now that is included in my spanning tree. Now remember, a tree can't have any cycles, loops, or multiple edges. So I couldn't use any edge that went back to B, for example, or back to A. That would not be a tree. So now I'm going to just show, let's see if we can draw from D, and we'll just reproduce this up to C. Okay, so just starting to build our spanning tree. Now I've got to look at A, B, C, and D, and what is the shortest edge that comes off any of those that doesn't create a cycle. So from C, I've got 8, I've got 6 here, 6 here, I've got 7, 6, 6. This one here looks the shortest, C to E, okay? Everything else is bigger than that. So this one will become the next edge that will be in my spanning tree, okay, going down to E. So I've got C to E equals 5. So let's just draw that on our little diagram down here. C to E, and that's got a distance of 5. Now I've got include E, so I've got to look at A, B, C, D, and E and find the shortest edge that comes off any of them. That one's pretty easy to do because I can see this edge here is only 2 units long. So that is going to be my next edge, E to F. And that will equal 2. So let's draw that in here. E to F is 2. And now I can stop because I've covered every vertice. I've covered A, B, C, D, E, and F. There are no more to cover. So I've got a spanning tree. It doesn't have any cycles. It doesn't have any loops or multiple edges. So it's a tree. And it goes through every vertex. So it's a spanning tree, and it is the shortest possible route between each of those vertices. So it's a minimum spanning tree. And if I was to say, well, how long is that minimum spanning tree? I just simply add up all of these numbers. 2, 5, 3, 5, and 2 gives me 17 units. So whether they were kilometers or meters or whatever it is. So I've now managed to find the minimum spanning tree for that network using Prim's algorithm. And it wouldn't matter if I started at a different point than A, I'd still end up with a 17 unit minimum spanning tree. In fact, why don't you test it? Why don't you pick a different vertice and see if we get the same result? All right, good job.